Right. So today we're going to talk about some questions that have shown up from your side as you were working on the fifth practical exercise, which was handling symbol tables in our compiler. So essentially, this is a complex task, as you've seen in the guidelines, and the guidelines might have maybe some smaller parts that were easy to misunderstand or misinterpret. So essentially, I thought I'd try to clear up some of the confusion that has arisen here. And this is just in order, I think, as they appeared on Piazza. So one question was about the cleanup task. So essentially, which is good practice, just after you constructed all the symbol tables you need, just cleaning up everything else which you don't need. And some of you found out that there was actually a mismatch regarding what function should be implemented in this cleanup task, because in the exercise document, we say implement the function destroy symtab to remove dynamically allocated symbol table data at the end of compilation. But in the guideline presentation, we say it's destroy subtree. Now, there's a guideline. So essentially, what in the guideline means that the destroy subtree function should be modified. So essentially, that was exactly what it was meant. So destroy subtree should be used to recursively just remove all the memory parts that were not needed. So that was just a simple, stupid typo. Okay. Next question was about initializing a global symbol table. There we asked you in the first task to initialize the global symbol table global names. But you found out that the skeleton file did not already contain any calls to TL hash init, which is supposed to initialize the hash table. And the question was how and where does the initialization happen? And you could, for example, call TL hash init in find globals, which is the function called from create global sum table. So that would be an appropriate place. And also, if you need an additional hash table, whenever you create a new scope, for example, when you detect a new function that was declared in your code. So there you could, for example, build a function push scope that builds the scope stack for your essentially stacked environments here. And in this function, you could also then create a new local symbol table containing a hash table with an initialization using TL hash in it. What else have we got? Another question related to TL hash init. How many buckets are we supposed to use in the TL hash init? Well, that depends on the number of entries you expect, obviously. And a power of 2 usually makes lots of sense. But feel free to choose whatever you think would be appropriate. Now, the problem really is that when you have a large number of buckets, of course, you increase the amount of memory the hash table takes. When you have a number of buckets in your hash table that's too small, then of course your searches take longer time because of essentially hash collisions, which require you to do a longer search on the linked list attached to each hash bucket. So essentially it's a trade-off, as in many problems in computer science. Of course, in general, we have very small example programs here. So I would guess for a real-world implementation, it actually doesn't matter in our example case. Then we had multiple questions by another group. The first one was about the sequence numbers, what exactly they are used for. Apparently, they're not needed for global variables. Should we set them to 0 then? Are they needed for all of the following functions, parameters, and local variables? So one important thing that we are going to use the sequence numbers for, and if I remember correctly, also for global variables actually, is to calculate memory addresses. So in VSL, we have only one data type, which is, well, if we don't count strings. So variables are, well, 4-byte integers usually. And so essentially, it's easy to create memory offsets of variables because each and every variable has the same size. Nevertheless, for example, we need to calculate stack offsets of local variables later on when we generate code. And we also need to somehow calculate addresses of global variables. So that's the major reason why we have these sequence numbers. Regarding nested scopes was the next question, that the proposed solutions to avoid name clashes. So to use a stack. So the stack then represents the nesting and enables us to walk the stack backwards. So upwards again from our most innermost scope to outermost scopes until you arrive at global variables when you're looking for a symbol. Should we implement our own stacks? Well, we haven't provided a stack implementation in our example code. So essentially, yes, you should create a very simple stack. So I could imagine you can do this using a linked list, which just each level of the stack then separately mallocked whenever you need it, and then you can free it whenever you leave this context again in your compiler. Another question here was regarding the linking of names to symbols. I guess that's what struct s pointer entry in node T is for. Yes, so struct s is a data structure for a general symbol table entry. So that's where it belongs. Oops. And another question was about the correct order to count, which is mentioned but not explained. Yeah, we thought that would be natural. So essentially, when you walk the syntax tree, you generate in the usual order, then essentially you get a natural sort of numbering. So I would expect actually this order to just derive more or less automatically due to the implementation of your parser and then the way you construct your syntax tree and how you traverse your nodes. So what we meant with this, don't try to like invent any unusual numbering or something special like generating random numbers or whatever you can imagine for generating numbers. Just use them more or less in the order they appear in the code when you walk your syntax tree. Okay, there's a question. I need to find my chat window. Should this be fine since we got an expected output example for this exercise? Yes, I think the question was actually well, how one could achieve to get exactly the order for the expected output example. I guess that was my interpretation of the question. But yeah, in any case, you have an expected output example. So if you're unsure, just compare your output to the expected output example, and well, you should actually figure out that there's no special magic in your compiler here. All right, what else did we have? What function should look at function parameters? So a long question. It's a bit unclear whether we're supposed to look at function parameters and find globals or in by names. Based on the task sheet, I would think that we should do it in by names. From watching the guideline videos, I got the impression that it was recommended to fill the function name table with the parameter names already and find globals. And the reason was that it would be convenient because it would save a second pass. So essentially, well, you have the choice to do this one way or the other. I think when we encounter the function declaration, we're still working on global level because all functions are obviously declared on global level because we don't allow for nested functions, just for nested contexts. So essentially, whenever we encounter a function on the global level, it's just easier because it really saves you a second pass. Otherwise, if you encounter a function and dig into the function, then you'd have to work on the local variables. But essentially, it's up to you. So you can do it wherever you like. And actually, one student group gave an example how they did it, and I took the liberty to just copy their answer here. So that student wrote that he or she opted to detect functions and find globals and process the functions in byte names. And in the current version that was delivered, that student called byte names when the code has detected a function node and find globals, and then passes a symbol t for that function node and the node t of the function node itself to byte names. And that gives the correct printout when using the skeleton code and compared to whatever example output we gave. So that's one way to do it. And I think that's probably not the worst way you can do it. What else have we got? End string lists. What's the size t end string list meant to be used for? It's, also that's not my answer. I think that was from one of our TAs or maybe a fellow student, but it's a good answer. So it's used for the capacity of the string list and set in VSL c.c. For example, here for initial size of 8 strings, and you can grow this on demand. So essentially, when your string count equals the number of string list, you have to resize string list. So this is a sort of a poor man's dynamic memory management for string lists, but it saves you the hassle of implementing more complex data structures for this. So I think that's a compromise to make programming that a bit easier. And of course, you need to handle the case that you run out of string space. But of course, if you wrote an early compiler for a small computer, like in the 1950s or 60s, those compilers could also just say like, oh, sorry, we ran out of string space in our statically allocated table. You cannot have more than 16 strings in your program. Now, that would obviously not be a good solution because we expect our programs to be a bit bigger nowadays, but still people did this. And in the worst case, if you can't get it to work, well, that would be a minor problem with the code. If you had a static allocation, would just complain if you ran out of string space here. But still, that's exactly what this is meant to be used for. You could also do it using just looking at the allocated memory size for a string list and then dividing it by size offs and so on. But that's just the easier way to do it here. All right, then we had something about string indexes, and I only had a quick look at that because that came relatively recently. So this group noticed that their tree dump of the file easy.vsl looks similar to the example tree dump, except that the strings in the string table have different indexes. And in particular, the string table starts with, I think that's a typo, the list of the strings from the second function, then it lists the strings from the first function, and the example tree dump does the opposite. If I'm not mistaken, that doesn't really matter. So this is probably due to your whatever ordering. Maybe, due to hashing that to tell exactly what's going on, I would need to see the code, obviously. So the order of strings in the string table is not important as long as the indexes are correct in the then generated symbols. Yes. All right. What else have we got? So we've seen quite a lot of questions that have shown up. We're having trouble understanding when we should declare functions in header files and when we should declare them just in the top of the C file. So that's a very general C programming question. First, we thought that the externally used functions should be in header files. This does not seem to match with the skeleton file, as there is a part of VSLC.c with something that seems like declarations that should be used externally. Well, in C, there are many ways to do it. And I think I also mentioned a bit about this, how to do this in the C crash course, and including hints how to use header guards to avoid stuff like multiple inclusions, stuff like that. Our skeleton code is a couple of years old, I must admit, so it's probably not the best C programming style. So essentially, feel free to do it wherever it works for you. So you can do it in both ways because, as you know, just inserting a header file using include is just a textual copy. So if you include it in your C file or in a header file you include, it will end up in your source code anyways. Well, you should just decide on an approach that really works for your case. That's more a general question of C program design. I'm not going into much detail here because we could talk about this for hours, I suppose. And it's a bit of a religious war on how to do things correctly. So I would say anything that works for you and compiles, obviously, and generates the right code is fine with me. But it's interesting to see because we're working on larger scale projects here. And that's maybe for some of you, your largest C project you've been working on so far, especially when you have to work with code written by other people. Then that's exactly the things where you need conventions for larger projects in order not to confuse your colleagues or maybe new colleagues coming in working on the project after whatever you've been working on that for a year. So it's important and it's a good question. It's a relevant question. And I must admit that no, our code is also not perfect. We've already mentioned that C probably is not the ideal language for implementing a compiler after all. So we're still thinking maybe of switching to a different language for upcoming years for implementing the compiler. This would require you to learn another language. So this is still under discussion. But for now, obviously, and what concerns you, of course, we'll just continue using C. Oops. What's going on? Okay. Now it seems to work. It has acted up a bit here. Another question was about destroy symtab. Is there any way to check that our destroy symtab function works correctly? Yeah, there was a proposal by one of our TAs that you can use a memory checker tool. So Valgrind is a tool that actually enables us to you to check for memory leaks. Valgrind has a problem on macOS 10 because it does not support the most recent macOS 10 versions. I'm working on a different problem where I would have needed Valgrind recently on macOS 10 to debug a problem in a multi-threaded just-in-time compiler that has shown up on M1 ARMMax. And there's other ways to do it. So there's debug versions of libc, which actually have malloc debugging. So something like that might also work, but it's not as full-featured as Valgrind. One hint is that Yak actually has some memory still referenced upon termination, like about 16 kilobytes. Some of this should actually still be noticed if you run Valgrind on this. And this, of course, assumes that you also free the static strings. Of course, in a small compiler, it doesn't really matter because, well, we have lots of memory for small compile runs. It's just a matter of style actually really freeing your memory, especially if you use this compiler in as a part of a larger program even, where you need different memory allocations. So yeah, then it might get more complicated. Final question, I think, was that the hash table seems to have returned broken keys. So this group found out that while destroying simple tables, they asked for all the keys in the hash tables like that. So they got the size of the hash table first, stored it in simple table size. Then they actually alloced an area of memory on the heap, which contains some table size, many character pointers, and then got the keys out of this with TL hash keys. And then they looped over all the keys of the hash table to retrieve all the symbols and to free what needs freeing. And they found out that fails pretty fast because the hash table seems to somehow screw up the retrieved keys with an example like this. Now, this is strange. That's an effect we haven't seen before, I think. So, of course, this then returns it causes a seg fault if you do a hash table lookup with the incorrect keys, because that fails and returns the null. So that's strange. We'll have to investigate this. So I haven't had time to look into this a bit closer here. So it seems that the keys are still intact internally. We can have a workaround, like you can get every value directly with t-hash values, can free those then, and you can then finalize the symbol table with TL-hash finalize. But to find out the error in the current approach, I think actually our code should work in most circumstances. Then we would actually need to take a closer look at what's actually failing. So I think that was all. Yes, those were the questions that have shown up. So I hope we could clarify a bit of this. And let's see what other questions showed up here. When will we get grades for PE5? Yes, when we have to grade it, we're working on it still. Sorry, that took a bit longer. As soon as possible. I know that's not satisfying, but yeah. I don't have a fixed date for this because I'm not the only one grading those, because yeah, and the other person grading this has been quite a bit busy. Another question: in the next exercise, would you be able to do a bit more descriptive variable names in the skeleton code? I find myself needing to go back to the different structures and methods because I don't know what the parameter variable is referencing, and it makes it harder to understand the code. Yeah, we'll try to do our best and maybe add some comments. Yes, that's a bit lacking because that is ancient code. This is in urgent need of a rework. Yes, I can completely understand that this is very desirable, and we'll try to add a bit to this to make it easier to understand. All right, so that's all from my side. I hope it helped a bit. As always, if there's questions, hit us on Piazza, send us an email. We'll hand out the next exercise, the hand-in date for that one, so probably next week, Tuesday. And of course, we'll extend the deadline appropriately for the final exercise. We'll also give additional hints for those of you using macOS 10 on Intel machines, because macOS 10 makes it a bit more complicated to generate working code. So essentially in macOS 10, it's not allowed. The linker refuses to actually handle global addresses. So you have to handle everything as a relative offset from a global pointer, which makes the generated assembly code a bit more complex. I'll actually have to, I think I found a way to get it to work. And if you actually happen to have one of the new ARM Macs, you still have the assembler and linker to generate x86 binaries, which can run in emulation. I know that's not satisfying, but at least it's a workaround for now. And for next year, we might be switching actually to ARM64 on Raspberry Pis for the compiler's course, but this is also still in discussion. Raspberry Pi maybe, or ARM64 makes the backend a bit, more convenient to write, I'd say, just because x86 assembler is pretty awful, at least from my point of view. All right, that's all from my side. If there are no more questions from you, thanks for joining the session. And well, see you next week. All right. Have a good weekend. Bye.